We assume digital infrastructure is universal, but for billions tracking cultural observances and historical anniversaries, standard software natively rejects the mathematical rules governing their timelines. Standard platforms, Google Calendar, Apple Calendar, Microsoft Outlook, are hard-coded to the Gregorian calendar. They operate strictly on a rigid, solar-based tracking system. This dual-axis timeline shows where the math breaks. A static Gregorian axis sits above the lunar Hijri calendar, which shifts 11 days earlier yearly. Adding a Hebrew axis introduces irregular lunisolar leap months. Finally, integrating Persian and Hindu systems reveals 4 precise chronologies entirely misaligned. Because standard calendar applications cannot natively process these shifting, multi-layered calculations, traditional dates are effectively severed from the digital workflows we rely on daily. Clicking Repeat yearly on a standard calendar event tells the system to lock on to a static Gregorian date. It is mathematically incapable of adjusting for lunar drift or lunisolar leap months. Consider Shia communities tracking FMB or ITS 52 Yarzites and Misak dates. The death anniversary of a family member might fall on a specific Hijri date, but its Gregorian equivalent will shift across the solar calendar year after year. Tracking observances requires users to consult external conversion tables, manually calculate shifting dates, and re-enter them by hand every single year. The standard market solution uses static file exports, typically a CSV or an iCal file. But a static file is dead data the moment it is downloaded. It covers a fixed time frame and immediately begins a process of decay, eventually running out of dates entirely. Multical functions as a synchronization layer between these systems, embedding the mathematical logic of traditional calendars into the API structure of modern platforms. To prevent the data decay found in static files, these timelines require a system that updates its own projections automatically as time progresses. The engineering dilemma becomes one of scale. Projecting shifting mathematical dates continuously into the future would normally require constant database processing, even for entirely inactive user accounts. Multical resolves this resource drain through a mechanism called the asynchronous trigger. This architecture diagram shows the process. When a user subscribes to a feed, their application automatically performs a background check to fetch updates. Multical handles this in 2 parallel steps. First, it instantly returns the current feed to the user's app, ensuring zero lag. Second, that same fetch request silently triggers a separate background worker to audit the user's timeline. If the worker identifies missing future years, it computes and inserts a rolling 5-year window of correct traditional dates based on precise astronomical rules. There is no manual intervention. Users do not log back into a portal to generate new files when their old exports expire. By utilizing the native refresh behavior of standard calendar apps, Multical creates a perpetual infrastructure. The act of your phone checking for updates causes the calendar to extend itself. Scaling this architecture from individual families to global organizations or historical genealogists requires processing hundreds of distinct cross-cultural events simultaneously. Allowing users to bulk upload CSV spreadsheets directly into a system risks UI clutter. A single malformed date string or a broken reminder setting can corrupt hundreds of entries on a typical user's calendar. This grid represents Multical's primary safeguard, the dry run validation table. Before data connects to the Google Calendar API, Multical parses the uploaded spreadsheet line by line. It scrubs for broken syntax, invalid emails, and structural errors, blocking uploads until the data is clean. Data entry relies on natural human language, which clashes with strict API requirements. A user might type a simple string like red or blue to categorize an event, which standard APIs cannot process. Multical's color and format parsers intercept these inputs. An algorithmic translation maps a plain text string like red precisely to Google's proprietary internal color IDs, such as tomato, ensuring the visual output renders as intended on the user's interface. This validation layer ensures human data entry is translated into executable code compatible with enterprise-grade platforms. Continuous synchronization creates a risk of state conflict. When a user updates a date or deletes a recurring traditional anniversary, the system must reconcile those changes across years of projected events. In background processing, in-flight errors or slight delays frequently leave behind orphan or ghost events. The old data fails to cleanly overwrite, resulting in a cluttered interface of duplicated entries. Multical manages this using a double sweep sequence. Initially, the system scans the API, locates outdated IDs, and purges historical data. To counter late write errors, a secondary sweep follows behind. It isolates lingering database orphans and removes them before inserting newly calculated events. This automated cleanup protocol guarantees the user's interface remains a reliable, mathematically accurate source of truth. Standard date converters frequently rely on default JavaScript math to calculate time. This creates a flaw. The resulting date can slip by 1 day, depending on the local time zone of the host server executing the code. Multical bypasses local server variables. It enforces time zone neutral UTC math at the database level, ensuring astronomical dates lock in with precision, regardless of geographic location. From asynchronous webcal triggers and data parsers to double sweep orphan cleaners and UTC integrity, the architecture is designed to handle this mathematical complexity invisibly. While simple conversion scripts exist, Multical functions as an automated infrastructure, maintaining cultural timelines with no ongoing user maintenance. The rigid design of the Gregorian calendar previously excluded these non-solar timelines from automated digital scheduling. The combination of UTC math, automated validation, and recursive background triggers allows cultural timelines to persist within a software ecosystem that was never designed to house them.